Professor Burley from New Mexico State University Mathematical Department with the talk Universality of Simple Cycle Reservoirs using dilation theory.
Thank you so much for the introduction. Thank you for coming here. So I'm going to talk about my recent project with the joint work with Robert Simon Fong and Peter Tino. They're from University of Birmingham in the UK. It's just on the sidetrack, Simon was actually my undergraduate friend. We were roommates for a year. And it's quite surprising how after so many years we come back all together and start to work on a project. So we both graduated from Waterloo. He did computational math as master, and he went to UK for his PhD. And we have been talking to work on something, and it's really surprising how we actually found something. He bringing in the machine learning part, and I bring some operator theory part. So I guess it's just a advice for our graduate student here. Keep your friendship. You never know what kind of thing can happen later on. So it's always good to keep your mind open and build up these connections. Okay, so I want to briefly discuss what are these reservoir systems in machine learning are, and then I'll talk about a little bit on the dilation theory and how they come in together. Okay, so that's roughly my plan for this talk. So let's start with the machine learning part. So in machine learning, well, it's a lot of this learning ideas. You have a bunch of input and you have a bunch of output. And your idea is you try to come up with something that connects your input and output. So if you have a new input, you'll get a new output. Okay, so there are several different ways of doing this. So for example, the first idea is you build some kind of more like a static learning. So you say, well, let's just forget about this as time series. We just look at this our input. There are going to be vectors in some Rn, and you have some output in some other dimension. And you can build things like a neural network. Basically, you just say, well, here's my input. Let's feed it into some signals, and let's try to connect them in the network. And I have output, and I try to optimize the connection and so on. So that's pretty classical. There's another idea is basically I treat all these as a time series. And when you have a time series, so the idea is, well, the B1 will kind of contribute to the Y1, okay, my output. But also my previous input are kind of going to have some impact on the output. Okay, so I need to memorize what happens in C1, and I also need to memorize a little bit of my history. Okay? I need to have some memory in this learning. So one common idea is you have a bunch of neurons, which is also a kind of time series. They're going to be called our states. Okay, so they're going to be some higher dimensional vector as well. So the idea is your new input will feed into your neurons, and your previous neuron will also kind of is the memory from your previous step, and it will contribute to your current one. And based on your current neuron, you output some output. Okay, so that's kind of the idea in these kind of learnings. So reservoir computing. So we're slowly moving into the simple cycle reservoir. So I'm basically explaining the letter R here. Okay, so what is a reservoir computing is basically the following. So the idea is exactly like this. So I keep track of the middle layer, which is our kind of the neurons. The C is going to be the input. Okay, so then my input, I'll map it using some matrix V times C of T. So I'll use this. So V times C of T. Oops. So V times C of T over here. Okay, so that's going to be the input. So I kind of map my input to a higher dimensional space. And I have my memory. This is the xt minus 1 part from my previous step. And I need to kind of decay it by a matrix W. And potentially I can feed it into some nonlinear function. Okay? And that becomes my new state. And based on this new state, I'll feed in some other function, I generate the output. Okay? So that's the reservoir computing. But the idea of reservoir computing was the difference is that this V, W, and F, these three functions, or these V and W, they are matrices, and F is a function. They are going to be fixed, right? So they are already fixed. So you're not going to change anything. There are some other ideas in the machine learning technique is basically you feed in the C and you map your C using some function, and then you try to optimize that function as you move along. So that B in that case won't be fixed. It'll be basically you need to train what that C should be. Okay, but here the reservoir computing is a little bit simple. Is basically you have this updating your memory card. That one is always fixed. Those the B, W, and F, they're always fixed. So you're not going to train anything. Okay, all your training is going to be in this H part. Okay, so H is the function. There's several different learning functions like sigmoid, those kind of functions. You put it into the H, and you try to train the H based on the output and so on. Okay, so all the training part are in H, and the X and C there, this kind of the dynamics is fixed. Okay, so we have this is called a reservoir computing. So these all have quite a long history. It's been here for fairly long time, and it's not really. It's only very recently when there's the next step is this linear reservoir system. It's probably the easier one of these reservoir computing. It's basically in the previous step we have a nonlinear function that updates my memory. And this is there's an F here. So in the linear reservoir system, basically you don't have that nonlinear function F. This function is gone. Okay, so your dynamic from the input to your memory is essentially just a linear system. Okay, it's a linear dynamical system. So this is what we have. So a linear reservoir system, basically you just determine by these three things: the matrix W, the input B, and there's a function that's you're going to train that one. Okay, so your input will be basically coupled, okay, by this matrix B. Okay, you convert your input into a state dimension, and you use your previous one and kind of decay it by this matrix W. And because you're decaying things, you don't want to make it bigger. So that's why we require this matrix to have a strictly less than one norm, operator norm strictly less than one. So the idea is your memory is kind of starting to fade eventually. Okay, so the xt minus 1 is your previous memory, so that will depend on xt minus 2 and so on. So as the time goes on and on, all the earlier memories are kind of getting worn, well, it's fading out. So that's basically captured by this norm less than 1. I have to say there are several other possibilities. Instead of requiring the norm less than 1, you can totally require things like its eigenvalue are always less than 1, absolute value of the eigenvalue less than 1, and those kind of stuff. They have some very similar properties, but for the purpose of our talk right now, we need this operator norm less than 1. Okay? We are working on some new ideas that relax this into some, basically relax it to the absolute value of the eigenvalue less than 1. Okay, that's actually doable, but we're not going to talk about today. And the matrix, we don't really have anything right now, and you have some continuous function, and we do need a continuous readout here. That's going to be important later. We always assume our input stream is uniformly bounded. That's a big assumption we have. So the CT, it's not a terrible assumption. I mean, most of the input, you're not going to input something really changing that much. Okay, so we also assume the input stream is less than equal to some universal constant. Okay, so that's a linear reservoir system. If you want to picture, the idea is basically you have your input on the top, the C. You have the output on the bottom, that's the Y. Okay, so each time when the C comes in, you multiply the C by this matrix B, you add it into your memory, and you get a new memory and you output it. Okay, and the next time you multiply your previous memory by the W matrix, and you add another input by this V, and you get a new memory, and you output it from there. Okay, so this is the linear reservoir system. Okay, so that's where it came from.
How about the H? H is given or you?
H is going to be trained, so you kind of assume certain form, like some sigmoid function, for example.
But the parameter is not determined.
Yeah,
form.
Yeah, the parameter are not
you
determined.
train for the parameter.
Yeah, exactly. Train for the parameter. Exactly. Yeah. So the H ones you have some specific form and then you have some parameter and you train it based on the Y. The key is the W and V are fixed. The H is the one you're going to train. Okay, so that's the only parameter in this model is this H. Okay, so there's no parameter in W and V. Okay. All right. So what is so good about this linear reservoir system is they are kind of they're in the theory of machine learning. There's this idea of the universality. Okay, so I'll briefly explain what they are. So universality, roughly speaking, I'm paraphrasing this work by these two persons. So they essentially universality is saying, so if I have some system, some different system, and I have another model like a linear reservoir, and how close can they get? Okay, so if I give the same input, can they get me the same output? Okay, that's roughly what the idea is. So it turns out the linear reservoir system are pretty much universal, meaning they can approximate anything. This is it's not a constructed result. You can approximate using several different ways. You can do it in the usual L2 norm or L infinity, and there's some LP approximation, those kind of stuff. Their proof mostly uses a Stonewall-Strass technique, so it's more like the existence because certain things are dense, and so instead of treating things like this dynamical system, you treat it as a kind of functional from some LP space. You take the LP of a bunch of all this input, the infinite series of this input, you put it into an LP space, and then you do the functional there, and you use Stonewall-Strass, and you can show they're going to be universal. Okay, so they're going to be dense. Okay, but in general, again, this is a linear reservoir system. How you can get a system that's kind of do what you want is still a very hard problem in general. Yeah.
Is there any idea on how big a degree the polynomial has to be?
No. That's the problem, I guess. Yeah. Yeah. So I don't think so. Yeah. Yeah. So it's more like existence. Like there exists one. Yeah. Okay, so but anyway, so linear reservoir, they are kind of useful because they're linear. Okay, you don't have on a nonlinear function in your dynamics, so things are slightly easier to understand. And they are, in theory, they can approximate anything in general, so that's why they're good. And I want to briefly talk about this linear reservoir. Really just become really popular in recent years because of this idea of echo state. So if you remember, this matrix W is basically the transformation of the state. Okay, so you have a bunch of X. Your X is basically an n-dimensional vector, is in high dimension. So in this picture, I'm just graphing what happens at the time t. So you have your input, should the C there. So your input is some, say, m dimension, and you transfer it into there. Okay, you get some n dimension, and you previously have X, which is kind of n dimension, and it is basically a bunch of numbers. And this W, what this W is doing when you do the matrix multiplication is you just move things around. Okay, so you have, for example, your first coordinate, you multiply by the W11, you get to the new first coordinate, and so on. So you can think about this W as some kind of connectivity in your neurons. Okay, how they connect to each other. So if your matrix W is non-zero in all the entries, basically what you're saying, if you imagine you do the matrix multiplication, you have n dimension. So each of these entries will contribute a little bit to each of the n dimensions. So you have a full connection. But in general, it turns out you don't need a full connection. Okay, so that's the idea of echo state network, is that you just let W to be a little bit less connecting. Okay, so in other words, in terms of matrix, it just means W has a lot of zero. Okay, so you have a lot of zero, meaning, like, for example, if you have a lot of zero, then this entry, this probably for example, if this is the first dimension, it only contribute to maybe like one other dimension, and maybe some two other coordinate will contribute to your first dimension. So there's not, other than that, it's all zero. Okay, so this is W make it a lot simpler if you have a lot of zeros. And it makes computation a lot easier because when you multiply a sparse matrix, you get something that's easy to compute because there's a lot of them are zeros. So this is called the echo state network. So that's the reason why the neural network, this reservoir system become really popular is really because of this echo state. They are very popular. They can do a lot of things, and it's just because computationally they're easier to compute. Okay, so now I will explain what the simple cycles are. Okay, so the simple cycle reservoir is essentially the easiest echo state you can get. Okay, so it's extremely restricted. So let me just recall, first of all, a permutation matrix is basically if you have a permutation in a symmetric group, then you have a bunch of 0 and 1 correspond to that permutation. So we just map, basically this is saying you map the ith coordinate into the jth coordinate. You basically have Pij equals to 1. That's going to give you a matrix, just 0 and 1. Okay, so that's a very sparse matrix, just bunch of 1s and bunch of 0s. And if your permutation start with just a full cycle, like n cycle in the symmetric group, then we call it a full cycle permutation. Okay, so you can just imagine as one way of writing a full cycle is like you have the 1 on the lower diagonal and you have an extra 1 on the upper right corner. And that's a typical full cycle permutation. So this is the permutation matrix. They're kind of the lowest connectivity you can get if you want to have a, say, invertible matrix W. Okay, so they have a lot of 0. So the simple cycle reservoir is basically one where you have the W is a multiple of this full cycle permutation. Is you have some constant in it because its operator norm needs to be less than 1. So D is going to be its operator norm. But the idea is you have this cycle commutativity basically. Okay, this is given by P. This is the minimum you can get. You cannot get lower than that. If you get lower than that, you kind of start to lose memories. Your matrix no longer full rank. Okay, so this is where the W is, and there's another restriction. This V part. We want this V to be something also a little bit more simple. I want it to be a matrix, just with interest plus or minus 1 or plus minus I. And here plus minus I really come from we're dealing with over the complex number. So if you're over the real number, we just do a matrix over plus 1 minus 1. Okay. So this is the simple as you can get for a kind of echo state reservoir system. Okay. So I just want to probably briefly mention this V. This requirement on this V is it's not that important, I would say. It's just we just put in there because historically people want that. There's actually some other restriction on this V. We want this V to be something that's aperiodic, so you're not really repeating yourself, but that's not too important in this talk. Okay, but anyways, that's roughly what the SCR means. So there, as you can see, this is the smallest connectivity you can get if you want to do any kind of echo state with invertible W. Why this is a good thing is that it's very nice for hardware implementation, and that's the good thing about these simple cycles. So there's a lot of people in physics tries to implement a reservoir system using some basically you build some computer chips to just do this one task of doing the simple cycle. Okay, so there are a bunch of people in Japan. So their idea is they use this architecture called the photonic computing. Okay, so you use photons. Okay, to basically shoot some light around, and you can imagine the reservoir is easy to. It's just a bunch of state, and you just rotate it. Okay, that's your permutation, and you always kind of rearrange your permutation to be just a rotation. So you have some input, you use some laser, you shoot around some laser, and you input into there, and you add up to your state. You do some stuff with your photons, and you have a bunch of output layer, and you try to train the output layer. So that's the training part. Okay, so the left hand side is going to be fixed, the right hand side is going to be trained. So that's roughly the idea. So they have a lot of different ways of implementing this. So there's some other architecture you can imagine. So I just took it from their paper. So this is so the idea is using these physical implementation of the simple cycle. You can usually make computation a little bit faster. And so a lot of the computation, if you use a computer, is limited by how many cores you have, the design of the chip. Okay, but if you do some very specific, specially built chips, you may get a higher, well, a faster computation. Okay, just because you're specifically designed for a task. Okay, so that's the advantage of studying the simple cycle reservoir is that hopefully someday people can come up with some of these implementation that make the computation faster. But I guess the immediate question is, well, what about the downside? Okay, so the question is, well, how well can we perform? Okay, how well can we perform? I don't want to restrict something so severe that we're not basically doing anything. Okay, right? You want your things to be useful in the end. Okay, so you want to make sure what you're doing is you can actually do a lot of tasks. And this is where my co-author came in. They have studied quite a lot of different applications of the simple cycle reservoir. It seems like it's performing fairly well, and that's where the idea originally came from. It seems like it's doing well. So the question is, well, is it going to be universal? Meaning, is it going to approximate anything in general? Okay, and that's just the goal of our research. And it turns out the answer is yes. It actually approximates everything, all the linear reservoir we have. Okay, so now, what do we mean by approximating linear reservoir? So we use the following definition. So if you have two reservoir systems, so our reservoir system are very simple. They're just a matrix W, a matrix V, and some function H. Okay, so we say they are going to be equivalent. It's just exactly what we expect them to be. So if your input are the same, I should get the same output, and then they're equivalent. Yeah, that's kind of trivial. We also call them epsilon close. If basically if you get the same input, then my output are always going to be within some epsilon. Okay, so so here remember our input stream is going to be uniformly bounded by some constant. Okay, so we're not we only look at those kind of inputs, and you can find some if you can find some, well, for any epsilon you can find, well, if there's an epsilon where these two outputs are always within for any of these inputs, okay, any of these inputs within this band, if my output are always within epsilon, then we say they're epsilon close. Okay, so that's very straightforward definitions. Okay, so the idea we're going to show is that simple cycle reservoir is going to be epsilon close to any linear reservoir, and that's our goal. Okay, so how do we do that? Let's do some warm up. Okay, so the kind of we get a feeling of what they are. Well, first of all, okay, so if what your linear reservoir, this is a linear dynamic, so the solution is fairly simple to write it out. Okay, so you have this dynamic, and it's very easy to see your x is essentially just given by this infinite sum. Okay, so you have a bunch of your input multiplied by the v, and you just decay by your w, and you add them all up. Because your w has operator norm less than 1, so this is well defined. So this summation will give you some vector. That's going to be the solution for your x, and your output is just plugging this vector into that h. Okay, so so we now convert instead of talking about reservoir all the time, we're now going to convert into a language that we know a little bit better about these matrices. Okay, so so the whole idea is basically how you can approximate this one. Okay, this and you can see that while the B and the C, they're kind of, the C is kind of your input, so you cannot do much about that. The V is always the V here, and the only thing you really can do something is about this W, or the powers of W. Okay? You want to do something about not just about this W, but also the powers of that. So the key idea is you try to approximate powers of this W. Okay, so that's the whole idea. And so let's do a warm up. Kind of what are some easy way we know about. So first of all, okay, you have a reservoir system. Well, what matrix trick we know? Okay, the easiest trick we learn in, like, you do the similar matrix. So If you have anything that's invertible, you can conjugate your matrix, okay, using the invertible matrix. And what you can do is you just put the S inverse multiplied to the V on the left. You compose your H, the output, with the S on the left, okay? And there you get another reservoir system, okay, given by this new matrix, another matrix, and your function is basically your original function composed with some invertible matrix, and they're going to be equivalent. And it's very simple. The idea is basically just we know that what the solutions are. This is the nice thing about this linear system because we already know what they are. So my solution is like that. If I put an S on the left, I put a conjugate here when I raise to any j. That's the beautiful part of the conjugation. The S inverse will go to left, cancel that out. S on the right, cancel that out, and you get exactly what we have. Okay. So this is the first idea we can have. Right? You can take conjugation of invertible matrix, and you can kind of have some freedom over your W. Okay, so you can, as long as they're similar, you can do this. Another thing is also fairly easy idea is it's very common. I mean, if you just perturb your matrix W by a tiny little bit, right? You let your W prime to be very close to the W. You keep the V and H the same. You get something that's going to be close. Okay, you just in the end you're just multiplying the W or W prime to some power. If they're close enough to each other, then well, their powers are kind of going to be close to each other. So you can always see they're going to be absolutely close when you have these two systems. So we have a little bit of room to kind of perturb the matrix W, and we can do some similar conjugation for this W. Okay, so this is some basic operation we can do. Okay. But they're not enough. Okay, the problem is this is not enough. Okay, so we need to do a little bit more than that. So this goes to a little bit of operator or matrix theory. So let's just recall a few definitions in matrix and operator where I came in. So if you have a matrix, or in general, if you have operator on Hilbert space, then we have a spectral radius is basically the maximum of the absolute value, or if you are a linear operator, you get the spectral radius, the supremum of the spectrum. The operator norm, there are several ways of doing the operator norm. You can treat it as just the S operator from L2 to L2. Or you can say, well, when you have a matrix, the matrix has a singular value. Basically, you take the W star the other way around. And you have a bunch of, it's a self-adjoint matrix, or positive self-adjoint. You take its eigenvalue, and there's the largest one. You take the square root, that becomes your singular value, and you have the singular value decomposition. So the largest singular value is basically going to give you the operator norm. This is another way of doing the same thing. So this is fairly well understood in matrix analysis. There are several ways to compute them. We say matrix is contractive, or operator is contractive. We use less than or equals to 1. I know a lot of when we talk about contractions in real analysis, usually we require strictly less than 1. But we take less than or equals to 1 for now. Okay, there's a reason for that. And among those contractions, there are several ones that are nice. Okay, one is the unitary one. Okay, they're essentially we're working in the complex domain. So if you take its complex conjugate, it's going to be its inverse. That's what it means by unitary. Okay, it's like the unit is like the invertible ones. The nice invertible ones are the unitaries. And of course, if you're in the real domain, this becomes orthogonal. You just take the conjugate. This becomes the orthogonal matrix. That's for real value matrix. Okay, so just a bunch of matrix we're going to work with. Okay, so what is the idea behind here? Okay, so let's look at what we have. Okay, so our system, really, we just need to work around this W. Okay, this W is where it's causing a lot of trouble. Okay, if I just start with a contraction W, this is where the linear reservoir system started. So what it is, well, first of all, if I just give you a general contractive matrix, it's very hard to say the structure of that. Okay, its eigenvalues, first of all, are, well, it's going to be in the disk, but it's hard to say where they are. Okay, that's the first one. It's in general not diagonalizable, so we cannot do those tricks, make it into a diagonal. I mean, you can diagonalize it into some specific form, but those are not easy to work with if you have, say, a Jordan block, then even if you take the powers of that, it's still a little bit hard to say what they are going to be. So they're not diagonalizable, and this is a problem. You may have another idea, well, how about we perturb it a little bit, we can get something better. But even that is not very easy. It's not even close to a diagonalizable matrix. And I think it's a fact from geometry, maybe. If you have a dimension that's higher than, I think it's 5 or 6, then the diagonalizable matrix are not dense in the matrix algebra. Okay, so you may not even be able to perturb it. Okay, it's not even close to a diagonalizable matrix. So they're very hard. Okay, so in general, we don't know how we handle a contraction. So on the other hand, unitaries are a lot nicer. We know its eigenvalues are always on the circle. Okay? They're not only that, they're unitarily diagonalizable. It's not only diagonalizable, I can find a unitary matrix to make it a diagonal. Okay, so that's pretty nice. So imagine you do the similar matrix, but a lot of times the similar matrix may be very hard. Okay, their norm itself may be hard, may be high. Okay, but it's unitarily diagonalizable. So this is a lot nicer. Okay, so there are the unitaries. So you see they have a lot better property compared to contractions. And the full cycles we're mostly interested in, we know a lot more about those. We know their eigenvalues are just a complete set of root of unity. We know how you diagonalize them. You know it's unitary diagonalizable. It's actually just do the discrete Fourier transform. That's how you diagonalize a full cycle permutation. So they're even better. Okay, they're kind of the best unitary we have. Okay, so the idea is we start with a contraction, want to move it to a unitary, and then we move it towards a full cycle, and that's where we're going to do it. Okay, so this is where this dilation idea came in. Okay, so what is the dilation? The dilation is you have an operator, you have a matrix, let's say, then you want to embed it into a bigger one with a better property. That's the whole idea of dilation. So for example, the easiest one is probably by Hamas. It's long time ago, the very early days of the operator theory. So if you have a linear operator or just a matrix, let's say, if it's operator norm less than or equal to 1, then you can form these two matrices. You have a dt here and you have dt star. They're not the adjoint of each other. They're just two positive operators. And you form a 2x2 block. That's going to be a unitary. Right? That's a unitary. So here I have identity minus tt star as a positive. That's a positive operator because t has operator norm less than 1, so that's positive. Because it's positive, in case of matrix, you can imagine its eigenvalues are all positive real numbers. So you can take the square root. Okay, so you can take the square root. That's going to give you the dt. In general, if you have in the Hilbert space, you need some continuous functional calculus, but it's okay. You know you can define the square root. And you also need a little bit of operator theory to see why this is a unitary. So here, if you put t on the left, and it can transfer to the right, but basically this is the dt square, and this is dt star square, and so on. That implies some inequality. But anyways, you can give that a check, and you can realize this is unitary. Okay, so this is a Hamas. But as you can see, the idea is we want to go from a contraction to unitary, but we also need to keep track of the powers. Okay? If you do this dilation of Hamas, you do the square. This t square, well, you have t square and you have a bunch of other stuff. Okay, so if you do the u square, the upper left corner is no longer a t square, so you lost your information. Okay, so we cannot really do that. So that goes to this another idea, very classical idea called Nash dilation. It's extremely useful in operator theory. And it says the following. So if you have a linear operator or just a matrix with operator norm less than or equal to 1, then you can find another unitary which satisfies this nicer property. You take the powers of u, and when you project back to the h and h corner, so you feed in an h factor, you project it back to the h, you get your Tn back. Okay, so in the matrix sense, is basically if you just keep doing if you imagine U as a kind of an infinite matrix where you have a corner corresponding to the h. Then you take the powers of this u, you will recover the t to the powers. Okay, so this is nice. And even better than that is that this u you can actually construct this. Well, Nash, when he first did it in the 53, he did more like a we call the GNS type construction. You can actually build something that's kind of show that it exists. But there's a nicer proof by Schaefer. Basically, you do the following: you just write out the unitary like that, and you show it's a unitary first of all, and you can see this is this t goes from the h and h column, and we put this 2 by 2 block not on the right hand side, but on the left hand side. So this dt star dt, they're kind of in the off diagonal a little bit, and this looks like the Helmholtz one, okay? And you put a bunch of identity there, okay? So the idea is you imagine you have a h vector goes in here, you have a t part and you have a dt part as whatever is left over. So you have isometry on this column, and because you introduce a new space for this dt, you need to take care of the vector coming from that, and you just keep shifting things around. Okay, when you're in infinite dimension, life is a lot easier. Just hide all the things you don't like to infinity. Okay? So this is why it's a unitary. Okay? This is why it's a unitary. Okay? So moreover, it turns out this is the unique or the smallest unitary you can get. If you do a little bit more careful job, you take this t, not make it h to h, but instead you take it from h to its range, and you put basically you add a little bit smaller space here, and you keep shifting a smaller space, then you get a minimal dilation. And the reason it's minimal is because all the unitary dilation, if you have a unitary dilation that satisfies the Nash condition, then it has to have it's going to be a direct sum of the minimal one with something else. Okay, so you cannot go smaller than that. Okay, so this is a very beautiful theorem in operator theory, but this minimality is kind of disastrous for if you want to do anything practical, because it means your U is infinite dimensional. Okay, that's a problem. You can never go into finite dimension because you can't. Okay, that's the minimum you can get is an infinite dimensional one. Okay, so we need a kind of mixture between these two. Okay, we need something better than Helmholtz dilation and something weaker than Nash dilation. And it turns out I was reading some other paper, and it refers to this result in 1954, which is kind of I would say this is the result is haven't really been touched for quite a long time. People haven't really do much on these finite dimensional dilational stuff. So it says basically exactly what we want. So if you just write a u, which is very similar to the Schaefer dilation, okay, you're not going to shift it to infinite. You only shift to finite dimensional steps, but you keep this kind of Helmholtz block on the upper right corner, then you get a unitary. Okay, and that unitary will keep your information of t to the power up to n. Okay, up to n. So you can do u squared, u cubed, and so on. You recover the t cubed and so on. But well, after n, you will forget about it. Okay? But that's not a big problem because my w itself is a contraction. Its norm is less than 1, or strictly less than 1. So eventually that itself is going to decay anyways. So we only need to keep track of my w raised to some finite power. So this is exactly the technique we need. Okay? So the first result we have is if you have any linear reservoir, then you can always find a kind of a dilation version of it. You dilate your state space to a higher finite dimension, okay? And this W prime is going to be a constant times a unitary, okay? And it has some other V and H, and the H prime and the H are not going to be very different. The H, you want to keep the H to be something trainable. This H prime is going to be trainable as well. You're just composing with some matrix, in fact. And the proof is nice in the sense it's actually a constructive proof. Okay? We can just, what we do is we want to approximate the sum, and we break it into a finite sum and the tail, which is small because W is decaying. And for the first part, we basically plug in a dilation. We dilate the W into W prime. We let Q to be my projection back to the original space, and the first n term will be exactly equal. And we forgot about the tail. Tail is small. Okay. So this is the whole idea. And of course, your B, you just feed in to to V and a bunch of zeros, so you see this is not terrible. The H is just your original H composed with this projection map. You have a higher dimension after this dilation, but you just project it back to your original space. Okay, so we can show they're arbitrarily close in this sense. Okay. All right, so from there, the next step is you move from unitary to cycle permutation. So this is the next result. You can kind of start with it. Once you start at the unitary line, it's a lot easier because its spectral property is nice. We can show is you can always perturb it. The idea is like a perturbation, okay? Because you're unitary, you know your eigenvalue are on the circle, so you just change your eigenvalue a little bit to match the eigenvalue for a full cycle permutation. Okay, so I'll probably just skip it and show you this graph. So the idea is the dot, this red dots are going to be your eigenvalue of your unitary. Okay, now they're now going to form a full cycle permutation on their own. But they're close enough. Okay? You can move them around by a little bit. If you want the better approximation, then you just add a bunch more higher dimension. But in the end, you want to move each red dot into a root of unity, into a distinct one. And you can do that if you imagine make your dimension higher and higher. Eventually, you're going to do that. And this is basically close enough to a permutation. Okay? So the whole idea, I will skip this part, but the whole idea is you can use some graph theory matching algorithm to see whether you can do that. And in general, you can just perturb your unitary into the eigenvalues of a permutation, and you may miss some other eigenvalues. You just direct sum a bunch of a diagonal matrix, and that's not going to cause any trouble. Okay. So once you match the eigenvalues, remember we can take the similar matrix, we can conjugate anything. Okay, and as long as the eigenvalue match, we can conjugate by unitary to get it back to the permutation. Okay, so this is the last step. So we have a full cycle. We still need to deal with this kind of annoying part where we want this V entries to be +1 - 1 or +I - I. I'm not going to talk how we did it. You just have to trust me on that. It's just some approximation idea. Okay, so you have this W is already a full cycle permutation. The idea is you kind of tensor it with another permutation. You get a bigger space, and if your V is not +1 - 1, you kind of use some simple function to approximate it. And again, another V prime. Okay, that's the best I can get. But anyways, that's doable in fact. So this is, you combine all of these together. This is our end result. So what we showed is that if you have any linear reservoir system over the complex domain, so meaning you have a W matrix just coming from a contraction, have a V and having H, then what you can do is you can always find a simple cycle reservoir that's close enough, epsilon close. Okay, so we first convert the W into a unitary, convert the unitary into a full cycle permutation, and then finally we fix the V part. Okay, so in the end, we show this is the universality of the SCR. Okay, so simple cycle reservoir, you can approximate anything, and that's going to be the goal. I just want to briefly talk about the real case. Okay, so a lot of time when you implement stuff, you don't like to carry around this +1 - I. So in the real case, I think they're extremely similar. There's a small caveat. The only thing is when you do the dilation, as we talked about the dilation part, instead of a unitary, you do exactly the same trick. You get a orthogonal matrix. Okay. So what we have, if we just rewrite our entire proof, we get a orthogonal matrix instead, okay, instead of a unitary. So that's not a big problem. The second step, when we try to perturb the eigenvalue of the unitary, before we're in complex domain, we don't really care. But we're now in the real matrix, so you cannot just diagonalize them because you introduce the complex number in the process. So what instead is that instead of perturbing the real orthogonal matrix, you have there is kind of diagonalizable. Well, you can diagonalize it in this form. You have a bunch of +1 - 1 as your those eigenvalues, and when you have a orthogonal matrix, you have a bunch of rotation blocks. These are 2 by 2 blocks. basically the cosine, sine, negative sine, well, so that's the 2 by 2 blocks. So this is not exactly their eigenvalue, but close enough. This is, you can find a real matrix S to diagonalize this. Okay, you can actually ask this orthogonal matrix. So you can kind of, it's not exactly diagonalized, but you put it in the standard form. And once you have that, the idea has become very similar. So instead of perturbing your eigenvalue, you know your eigenvalue come in blocks, so they correspond to a rotation. So let's just perturb the rotation to a rotation that's 2 pi divided by n, some multiples of that. Okay, so you perturb the rotation, it becomes a little bit more tricky how to handle those multiples of plus or minus 1. But in the end, you can do that. Okay, it's doable. So you can perturb it to another kind of canonical form for your full cycle permutation. And then you do the similar matrix again, you move it back into the full cycle, and all this process, you're not really introducing any complex number. Okay, so in the end, what you have is just a real version of the linear reservoir system. Then you can approximate using a real simple cycle reservoir. Okay? Meaning all the stuff that you're not going to introduce any complex number in the process. Okay, so this is another result we have. And I just want to probably briefly mention what is this research? Where does it fit in the big picture of things? And we're doing a lot of theoretical work. So the whole idea of these machine learning is that you have some problem using a time series. That's where we started with. Okay, and people use some linear reservoir to solve this problem. And this is, you try to find a reservoir system that solves the problem. And what we did is essentially saying, once you know how to find a linear reservoir, you can use our technique to convert it into a linear reservoir where you have a simple cycle instead. Okay, so you don't have a random, a weird matrix W and B where you have really no control with, but you really have a simple cycle, which is a lot easier. And hopefully use some hardware to implement this simple cycle reservoir. There are a lot of groups doing these. We're not doing that. Okay? But hopefully one day someone will say, well, if I have a simple cycle reservoir, I can build a hardware, I can build some machine to compute it pretty fast. And that will help us to solve our original problem. Okay? So in the grand scheme of things, this is what we have done. Okay, so I think this is a good place to stop. Thank you.
That's back to your beginning question. So, how do you train to get the parameter about the edge?
How do you train? There's several different techniques. You do the gradient descent or something. So the idea is this. You can think about the training part is. Let's try to find our stuff. So in the very beginning, so your dynamics is essentially here. You have a x and h is the function to train the output. So you have some training set, and you just instead of training it on the idea, I guess, is instead of training on the input, you train it on a bunch of these neurons, and you do the
so
whatever.
You have a goal function, or you have a goal to train to let the edge.
Yeah, so the y is
otherwise how do you
so you are given an input string and an output string, so b and y are known. So you use your reservoir to generate a bunch of signals, that's the x, and you train from x to y using the whatever the several techniques.
The purpose is to figure out the edge.
I mean, the H is not a terrible thing to figure out. There's several packages, for example, Python can do it for you. If you just tell Python, I have the input and I have the output, and I have a kind of layers of neurons. I want H to be this format. Python can usually train it for you. So that's not a terrible part.
Yeah. So if you start with a system of size d, now if you're given epsilon, say 1 over n, the idea to change it is you increase the dimension.
Right. Yeah.
Now, the smaller your epsilon, so in other words, the bigger the n, probably the bigger the increase in the size.
Exactly.
What's the relationship between these two things?
Yeah, this is we do have some bound. Again, it depends on the epsilon for sure. I think we did some experiments. So if you start with something like a dimension, it goes to a few hundred dimension, depending on how well you like. So right now the theoretical dimension is pretty high. So there's kind of three procedures where you increase the dimension. The dilation, that dimension you cannot really change much. It's just dilation. The second part where you do this perturbation of the eigenvalues. So this part is the second part where increase dimension. This part we can do a little bit better than our theoretical one. So theoretical one is just you inflate it to something like n squared, and it's super ugly. So in reality, if you do this another algorithm using some perfect matching algorithm, it's not going to be terrible. I guess you multiply the dimension by several times, 4 or 5 times, but it's not going to be like n squared, those kind of things.
Oh, so it's linear, roughly.
I have no idea. In general, what it is, I don't know. Yeah, that's the short answer. Theoretically, you can always do one with something like n squared times some other constant maybe. But in practice, we don't really know what's the best one we have. We have some simulation, but we don't know what happens if you want to go further.
Okay, thank you.
And there's, I guess, another thing I want to say is we also want to do something. So once we have a SDR in the end, there's some other way we can, you see, we're just doing a lot of matrix tricks, and there's some other matrix trick we can potentially play to get down the dimension. So that's certainly something we do want to do eventually, to lower our dimension, because we kind of increase our dimension quite a bit.
Oh, I have a question. So, it's a vague question. Is there a counterpart of this in terms of symbolic dynamics, when instead of R real numbers, you work with quotients, like finite alphabets representing your
Yeah, I'm not entirely sure. Yeah. Now where I mean.
Can you, oh, this is something else. Can you, I mean, create a new courses called machine learning? I will be the first student.
Yeah, I'm happy to, I think, yeah, so a lot of these, I learned some of these from, there was a open course online I learned before, so I know the training from the H part, I use backward propagation of kind of technique. So those are fairly standard, yeah.
Then you can make a class.
Yeah, I'm happy to.
We like the young people though.
Is it true that in the machine learning course, every next course should be different?
Oh,
What about global? We can distribute
Thank you.
Pardon.